Good day, class. So for today, you're going to model other physical systems using first-order differential equations, then derive their transfer functions, and after which predict the responses to the various types of input disturbances. So we're going to look into each system one by one, and we're going to start off with the liquid level system. For this system, you're given a liquid inside the tank with level H, and the flow rate of the liquid entering the tank is Q of T, and the volumetric flow rate out of the tank is Q sub O of T. Now, the flow out of the tank is passing through a linear resistance R, and this is a flow resistance that may be offered by a pipe or by a weir or even a valve. So anything that offers resistance to flow is represented in this case by letter R. Now, our Q sub O has a linear relationship with the head, and then in this particular linear relationship, you have the incorporation of the R. And that equation is given by Q sub O being equal to H divided by the R. So it's a linear relationship with the reciprocal of the flow resistance as the slope of the line. So the head is directly proportional to Q sub O, and its relationship with it is linear. Now, what causes our output Q sub O of T to change is the changes in our input, which is Q of T. So our disturbances in this case will be coming in the form of changes in the Q of T, which will bring about changes in the Q sub O of T. Now, prior to determining the transfer function for this liquid level system, we need to have special assumptions. We need to assume things, that way our modeling would be made simple. And there are two assumptions needed here. So the first one is that the cross-sectional area of the tank should be a constant, in the same way that the density of the liquid inside the tank should also be a constant. So this too is assumed to be a constant. When we model, we start off with the differential equation representing the unsteady state mass balance of the liquid inside the tank at any particular time. And it is given by this worded equation that the rate of the accumulation inside the tank is equal to the rate in which the mass is coming in minus the rate in which mass is coming out. In the original DE, wherein we need to determine the amount of material that is present in the tank at any particular time, which is the rate of accumulation, you have the density in all the three terms here. So you have A rho dHdt on the left side, then you have Q rho minus Q sub O rho, where rho is the density. In this case, it gets cancelled out because of our assumption. So if we hadn't made that assumption, then we will be having densities in all the terms of our differential equation here. Now, at steady state, we have to also know that your Q would also be equal to Q sub O, or shall we say your Q sub S, which is the Q at steady state, is equal to the Q sub OS, which is the Q sub O at steady state. So this is only for the special case of steady state condition. So now we will derive the transfer function for this liquid level system, starting off with the differential equation written here. And for the rest of the derivation for the other physical systems, I'm referring to the derivation for the transfer function. I leave that to you to study on your own, and this would be your baseline of the principle behind the derivation of the transfer function of any physical system. So we're going to do that. So we're going to start with the differential equation that we're going to use in this case in determining the transfer function of our system. So we're going to start with A. Okay, that's our A. This would be now the volume accumulated at any particular time in the tank, and that would be equal to your Q minus your Q sub O. That's our start of DE. And then if we will evaluate this at steady state condition, the left side would be a 0, and the right side would have the subscripts S for your Q and your Q sub O. Now, if we will get the difference of these two, you will have A dH dt being equal to Q minus QS. Then you can place a parenthesis here, minus Q sub O minus Q sub OS. Now, if we will represent by deviation variables these two differences in the Q and the QS and the Q sub O and the Q sub OS, then we can represent them as big or capital letters. So we'll start with that, of our small letter variables. Then we will do the same for our Q, and that would be small q minus small qs. Now we will go back to our original representation and we will write it as dH dt equal to Q minus Q sub O. Okay? Now, but we remember that we have this linear relationship between Q sub O and the head. So we can use that. But Q sub O is equal to your head divided by the linear resistance. This was originally written in small letters, but you can convert it to capital letters if you evaluate the original expression at steady state, and you will subtract that equation at steady state from the original equation, giving you this one, the Q sub O equal to capital H over R. Now, you may wonder why this one is already made capital, wherein in the original, it's only small letter h. It's because, if you notice, this D capital H is the D of small h minus hs. If you're going to perform differentiation to these two terms here, and this being a constant, this will be equal to 0. So your D capital H is just equal to D small h in that case. So what I did here was convert right away the D of small h to the D of capital H. And we have this. Now from here, since our variables are already deviation variables, we are ready to get the Laplace. So if you're going to get the Laplace of this, you will have, for the left side, A S H of S, and the right side you will have Q of S minus Q sub O of S. Okay, they are all functions of S already. However, our problem here is that we have 3 variables, and there's a need for us to only limit our variables if we have to derive the transfer function of a physical system to only 2. So we will be changing one here in terms of another, and what we will be changing is this Q sub O of S. Why? Because we have this relationship that our Q sub O is equal to H over R, and we are going to apply it here. So we will continue what we have started off. So you have A S H of S being equal to Q of S, and this Q sub O of S will be your H sub O of S over R. Or sorry, that's not H sub O, but rather only H of S. Okay, now you have H of S here and H of S here, so you have to group the two together, or combine terms that have similar expressions in H of S. So you will have something like AS H of S plus H of S over R equal to Q of S. Then we will factor out H of S in the left side, giving us AS plus 1 over R being equal to Q of S. Now what happens, we will simplify this and we will copy only the H of S. What we have here is ARS plus 1 over R, and this is equal to Q of S. Now, if we will represent this AR by tau, so if we will represent the time constant of our system as the product of the cross-sectional area of the tank and the linear resistance to flow, this particular equation now can be rearranged so that it would look like a transfer function. So the transfer function as defined is the deviation of the output over that of the input. So we take the Laplace of the deviation of the output based on the changes in the input. So we will rewrite this expression incorporating already the tau. In that case, our output is the head, and our input is the Q, because your Q is changing and it will bring about a change in the level, and that would be equal to, so if we go back here, if we transfer the Q of S here, this one goes there and this one goes here. So that would be now giving us an R over A RS plus 1. Your R is equal to tau S plus 1. Now this is the transfer function of a liquid level system. The gain, this one, is the linear resistance to flow. The time constant is tau, which is the product of the area and the linear resistance to flow. Our first order systems always have this form in the denominator. So the denominator for our first order system always has this form, the tau S plus 1. They will only differ in the numerator. So this is how we derive the transfer function of a first order system using Laplace transforms or using Laplace transforms in evaluating differential equations that were used to model the system. So for our liquid level system, if we're going to go back to that, the transfer function now is the one that you are seeing there in the derivation. So H of S over Q of S is equal to R over tau S plus 1. And that would be the transfer function for our liquid level system. Okay? Now, in terms of there was this mention about linear resistance to flow. So it could be a pipe, it could be a contoured weir or a sutru weir, or it could be something like, or anything like the expression wherein the level of the liquid will have an exponent other than 1. In terms of the linear relationship, it's not anymore linear once we change the relationship between the Q sub O and the H. So here, the H is already having an exponent of 1/2. If that is the case, your relationship with Q sub O and level is not anymore linear. So that is the case, then we will be needing what we call a linearization procedure, which will be discussed in the latter part of the slide. Okay, so your Q sub O is only linear when the problem states that it is linear. If it's not, if the problem gives you a Q sub O relationship wherein the H does not have an exponent other than 1, you cannot go on with the derivation that was illustrated to you a while ago. You have to first do linearization, then derive the transfer function. That is in terms of our liquid level system. So if we have now the ready-made transfer function for our system, that would be R over tau S plus 1 for our liquid level system. So R is the steady state gain. I've mentioned that already, and it's the ultimate change in the level. H for a unit step change in the Q of T. So take note, for a unit step change in Q of T, that would be the ultimate change in the level. Now, this would be our formula only for a liquid level system for the time constant. Now, it could be that we want to have a relationship between Q sub O and Q, not H and Q. So, it's like this. Now, how did this particular equation came about? So, we will go back to our board again. So, our original transfer function is R over tau S plus 1. This is the original. So we'd like to express this H in terms of Q sub O. Or rather, in terms of, Q sub O. There's no need to erase. The volumetric flow rate out of the tank through the linear resistance R. So we want it like this. So how do we do that? So we look for a relationship that we can substitute here, that we can place in here. So we go back to the linear relationship between Q sub O and H, and that relationship was already given here. Where is that? This is the relationship that we're talking about. So from here we can get the relationship that H is equal to R times Q sub O. So if you do cross multiplication, you will have an expression for the level in terms of the volumetric outflow from the tank. So we'll go back to our equation, your original transfer function, and we will replace H there by its expression in Q sub O and R. So in this case, we will have this H now changed to Q sub O of S times R, as shown to you, over Q of S is equal to R over tau S plus 1. Now this H of S is this one. Our goal is we will have this expression. So we cancel the R's. That gives us a left side, which is Q of S over Q sub O of S over Q of S being equal to 1 over tau S plus 1. So that's the new transfer function from the original transfer function for the liquid level system. And that's this one. Okay? Now, in cases wherein we have constant flow out from the tank, it's because the flow is regulated by the tank. So meaning it's fixed because there's a pump that regulates the flow. The transfer function for our liquid level system is simplified in this form, which is 1 over AS. Now your Q sub O in this case is a constant. So this is only limited in cases wherein the flow from the tank is regulated by a pump. Okay, so that's in terms of our liquid level system. So we have 3 different transfer functions for the liquid level system. One, the original, which is R over tau S plus 1, which relates head to changes in the volumetric flow rate into the tank. The other one is 1 over tau S plus 1. This is in the case of relating volumetric flow rate out of the tank to changes in the volumetric flow rate to the tank. And the last is when the flow rate out of the tank is constant, in the case of a pump regulating it. Now, another system that we will look into is the mixing process, wherein you are homogenizing a particular mixture here, and as a result of this homogenizing process, you will have a mixture in the tank having the same concentration as the mixture of the fluid leaving the tank. So whatever is the concentration here, that would be the same concentration of the fluid that is leaving the tank. So in this sense, your X and Y now are to be viewed as the concentrations. So X is the concentration of the fluid entering the tank, and Y is the concentration of the fluid leaving the tank. Both are in terms of mass per unit volume. That's the way we express concentration in mixing problems. Now the Q that you are seeing here has to be constant. Otherwise, our tank will either overflow or dry up. So this 2 is fixed and it's a constant. Now our assumption, so that one included the volumetric flow rate being constant, we are also assuming that constant man ang volume. It's because the volumetric flow rate is also constant. Then we are to assume as well that the density of the system will not vary for this mixing process. Now our mixing process also starts off with the steady state mass balance, wherein we are accounting for the accumulated mass inside the tank based on the difference of the mass entering and leaving the tank. So if we're going to write the difference differential equation appropriate for this worded unsteady state mass balance equation, that would be the volumetric flow rate to the tank, which is constant at Q, and then they're being multiplied to the X and Y. So X and Y, X for the concentration of the fluid entering and Y for the concentration of the fluid leaving. The accumulated volume inside the tank at any time will be the product of the volume. The accumulated mass rather is the product of the volume and the concentration of the liquid inside the tank at any time, which is Y. So if this is mass over volume, I'm referring to the Y. If you're going to multiply it with the volume, that would be mass over time. So your accumulated expression here in the derivative is mass over time, in the same way that this too is also having unit of mass over time. Since volume is assumed to be constant, we can write it before our derivative, and that would be now giving this as V equal to dy dt, or the derivative of the change of the concentration of the fluid or liquid inside the tank at any time. Now at steady state, we will evaluate these three terms here, and that would be Qxs minus Qys on the left side, where S represents steady state values for X and Y respectively. And since at steady state there won't be any changes in the concentration inside the tank, that would be 0. Now if we will note that deviation variables are represented by capital letters X and Y for concentration of the fluid entering the tank and concentration of the fluid leaving the tank respectively, then if we subtract the second equation from the first, it will yield this particular differential equation. Just like in principle, the one that was illustrated to you a while ago in terms of also deriving the transfer function of a liquid level system. So this is the dE that we have here for now. A dE that has the concentration of the liquid coming in and the concentration of the liquid leaving the tank at any time. So for the mixing process, if you're going to perform Laplace transform for this expression, you do Laplace transform here with Q and V being constant, then this would be X of S, this would be Y of S, and the Laplace transform of dy dt in this case would be S Y of S in here. Our transfer function resulting from that process will be 1 over tau S plus 1. So for a mixing process, the transfer function is the concentration of the liquid leaving the tank over the concentration of the liquid entering the tank. The changes of the two wherein we took the Laplace transform of. The form of the equation is similar to the first one in the denominator, just like what I have mentioned. The only thing that is different here is the tau. The tau for the mixing process is V over Q. Okay, so this is our transfer function for our mixing process. Now for the stirred tank heater, this was not mentioned or this was not discussed in the previous CHE 33 courses, but it will be included now. We are also taking into account the accumulated, not mass, but rather energy of the fluid inside the tank. It is now the energy that we are accounting for because our system, the fluid, is being heated. So the rate of accumulation of energy in the tank would be the rate of energy flow into the tank minus the rate of energy flow out of the tank plus the rate of energy flow in from the heater itself. So what is the amount of heat that is being introduced into the fluid from the heater? So if we're going to convert our worded energy balance here on top into an equation, it will be using the MW here is the mass flow rate of the fluid, C is its specific capacity or specific heat, and you have T sub I as its inlet temperature, and this T sub RF is some reference temperature that we're going to use. So this is the energy of the fluid coming in, this is the energy of the fluid coming out, and this is the energy inputted into the system by the heater. the rate of accumulated energy will constitute the product of the density, the volume, and the specific heat capacity of the fluid, and dt minus T reference again. But since the value of the, or rather the derivative of a constant, which is the reference temperature, is 0, then this right side here is simplified into d capital T, d small t. So T ref here is the reference temperature and C is the heat capacity of the fluid, just like as I have mentioned. If this equation 1, which is the energy balance from the worded and steady state energy balance that we have here as a guide, if this is evaluated at steady state condition, the right side here becomes 0, and this 2 is combined with the T sub I S minus TS, and you have here the QS. It can be written in this form. Now, why do you think that we have this representation here? If you're going to combine these two, this T reference will simply get cancelled out. They will just get cancelled out. What is left is the T sub I and the T here. And since we are evaluating at steady state condition, the T sub I will now be T sub IS, and the T would be the T sub S in this case. Okay, I hope you get that. So if you subtract these two, your T reference will get cancelled off, and since it's to be evaluated at steady state, your T sub I becomes T sub IS, and your T becomes T sub S, and the right side becomes 0. Your Q is also labeled as Q sub S, since this is at steady state. Now, if you're going to subtract 2 from 1, just like what we did in the 2 physical systems, this would be the resulting expression. Okay? You subtract this from the original, this would be our resulting expression, equation 3, which brings about, again, the incorporation of the deviation variables T prime for T minus TS and Q for Q minus QS. Now, our equation 3 from the previous, this equation, is simplified in this form using deviation variables. So if we take Laplace of this expression in equation 4 rather, it would be copying only the other characteristic parameters, and all the variables will have S. It will be converted as a function of S. So the T prime of S, the Q of S, and the T prime of S in this side. Now, again, if you may wonder why the original DE here, which has 3 terms on the left, was now only written in 2 terms. 3 terms original, and now you only have 2 remaining. It's because of this assumption. We need to assume that there won't be any changes in the inlet temperature. That way, we can have only a DE wherein we're only going to relate 2 variables. If we will not assume that the inlet temperature will not change, we will have 3 variables, and it will not make it easy for us, or it's impossible rather for us to derive the transfer function if we are relating already 3 variables. So we only need to have 2 variables for us to be able to write the transfer function of a system. So this is just but an example wherein the changes in the inlet temperature is negligible. If we want it to do it the other way around, wherein it's T sub I that's going to change and Q will be the one that is fixed, then we will have a different transfer function. It will be a transfer function wherein the outlet temperature will be related to the changes in the inlet temperature, because we have assumed that the amount of heat supplied by the heater to our system is not changing, or it is constant. So from equation 5 that we have here, wherein we have already taken the Laplace transform of 4, we will have, after rearranging of terms, a transfer function for our heater. a tank heater wherein the fluid is being heated. Again, the denominator, if you notice, has the same form with the two physical systems discussed. That is the liquid level and the mixing system. The steady state gain in this case is the K. What is this K? It's based on the values that you have simplified in here. So, if rho V over W is the tau, then your K will be 1 over WC. Or your K, the steady state gain, is the reciprocal of the product of the mass flow rate and the heat capacity of the fluid. The tau for the stirred tank heater is the rho V divided by the W. And that is for our stirred tank heater. So we have already 3 systems added to the first, which is just but a simple thermometer that will illustrate your understanding of how you're going to predict the responses of your system would be based on the different types of input disturbances. I have mentioned in the resistance to flow that at times the relationship between head and Q sub O is not linear. In that case, we cannot go on in the process of our derivation because Q sub O is not linear in its relationship with H. In that case, there's a need for us to linearize. No dynamic system can be characterized if it is non-linear. So there's a need for us to linearize, then that's the time that we can get its transfer function. After getting the transfer function, then we are ready to predict the different responses based on the different types of input. Now, a classic case or system wherein the method of linearization is being used is in the case of a pump that is being used to dispense the fluid from a particular tank or container. Now, in here, we can say that the volumetric flow rate through this particular resistance, which is the pump, is C square root of H, just as an example. Now, in this case, your level H does not have an exponent, which is 1, which should make it linear. So, any other exponent would make it already non-linear. So, the relationship now, if we're going to plot between level and Q sub O, is something which is curved. Now, we cannot derive the transfer function if that is the case. So, we need to know how to linearize. And that's the thing here that we're going to do now. Now, we have to remember that this is our relationship for the head and the volumetric flow rate out of our system, our tank. And if we're going to write our mass balance again, our unsteady state mass balance, just like what we did in the liquid level system, your Q sub O, this should be QI or Q minus Q sub O is now this Q sub O. So it's not the Q sub O, which is a simple case of H over R, but rather it's C, a constant, which is a characteristic or property of the valve or of the pump or whatever linear resistance that be, times 2 the square root of H. So this is now nonlinear. So we cannot go on. So we need to address the problem of this term, which makes our DE, or equation number 2, nonlinear. And one way of doing that is by using what we call the Taylor series expansion. We use Taylor series expansion to find an expression equivalent to this nonlinear term. That expansion has our original variable equated to that particular variable wherein it is evaluated at steady state conditions. So this means that your Q sub O will be evaluated at the steady state level of the liquid, or we evaluate it at its steady state condition because this Q sub O in the first place is only dependent on the variable H. Now, since H has a subscript S, it's just like interpreting this expression as evaluating it at steady state condition. It will be followed by terms now wherein you are evaluating the same formula or expression, but this time not the expression itself but its derivative. So in the second term here, that will be the first derivative multiplied to the deviation form of the variable H, It's h minus hs. And then the next term will be the second derivative, evaluated also at steady state, just like in here. But this time, the difference between h and hs, our deviation variable, will be raised to 2, and it will be divided by 2 in here. And then this will be unending until infinity, because Taylor series expansion is actually an infinite series of terms. But there's no need for us to write so many terms in here, because anyway, the terms that would be appearing in here are nonlinear once the exponent of the h minus hs is other than 1. So in this case here, the third term will be neglected, will not be accounted for, because that makes our equation here nonlinear already, because the h now has an exponent of 2. So we will only consider as a substitute for the second term here in equation 2 the first two terms. Now, if you're saying, then it will not be accurate, because you have already taken out of the picture the derivative of the q sub o multiplied to the other deviation variables to raise to a certain exponent. Actually, you are right. It will not be as accurate if you will be considering everything. But nonetheless, class, if you notice this deviation, if you're going to raise it to a higher exponent other than 1, that makes this particular term nonlinear. And our goal here is to make a replacement, or to look for a replacement of this which is linear. So that is why we are to neglect the other terms. The values of this, if evaluated, since this is already second derivative, the next would be third derivative, fourth derivative, fifth derivative, and it would be factorial, by the way, in here 2 factorial, then here 3 factorial, and so on and so forth. The denominator is increasing. And if we increase the divisor, the value of anything decreases. So the value that you are adding actually in this infinite series of terms would be very small. So that is why it's okay even if we take them out of the picture. So now we will only keep the terms that are linear. So that would be the first two in here. What do we do with the first two? These first two will replace the original. It should replace the original, and we will evaluate the q sub o here in terms of its derivative, because it's needed here. You could see that you have q sub o prime of h of s. So meaning you are to get the first derivative of this, which is this one, and plug it in here. This is already evaluated at steady state, so you are to plug it in here. And once this is done, this q sub o prime of h of s being substituted here, the entire equation 3 changes, and once it is changed, you go back to the original equation 2 to have your dE now, which is made linear in form. So this would be your q being equal to q of os plus h minus hs divided by r1. Now it's defined already that your q sub os is your q sub o at h evaluated at h sub s, meaning the q sub o at steady state condition. This is already it. And the 1 over r1 here is already this set of constant, because you could see it in here that you have this set of constant 1/2 c h sub s raised to negative 1/2. This h sub s, since this is the level at steady state, it's a constant. So we can assign a new constant for this, and that's what is done here. So it was assigned a value of 1 over r1. So if we will substitute equation 5 to the original equation 2, which is nonlinear, this is our nonlinear equation. If we will substitute equation 5 to it for the q sub o, the q sub o here, which is nonlinear, your original equation is converted in this form. Now it is linear. All you have to do is make sure that this q sub os is changed to qs, because anyway at steady state your qs and your q sub os are just equal because it's steady state. So you change this one to qs. So now your equation 6 becomes this one. The q sub os here is changed to qs. This is your equation, which only needs the replacement of the h minus hs here and the q minus qs here and the small h here, two deviation variables which are already made capital. Okay? So if it's done already, as I have mentioned, your equation 7 is converted into this form. Now you have determined the transfer function of a nonlinear system using the process of linearization. But let's define what we have for R1 in this case. For our liquid level in which the relationship between H and Q sub O is not linear. So your R1 is defined as this one. C is any constant that appears before the H in the equation Q sub O equal to C square root of H. So it could be any number here. And your tau is still the product of AR, but now it's AR1. In the case of this particular type of system, wherein the relationship between Q sub O and level is not linear. So now you have learned 4 different derivations for the transfer function of a system which is said to be linear and non-linear. So all in all, you have learned already 5 different transfer functions. That for the thermometer, that for the liquid level at 3 different cases, that for the mixing system, that for the stirred tank heater, and this one wherein you need to linearize. Actually, this covers everything about other physical systems modeled using a first order differential equation, derive the transfer function, and determining the responses to the different types of input. Now, there are systems which are said to be regulated and non-regulated based on the manner that they respond to the different types of disturbances. So we say the system is not regulated, or we have non-regulation when it is a condition where the response of a system grows without limit for a sustained change in input. If the change in the input is sustained, but your response is let's say increasing infinitely or decreasing infinitely, then it is, shall I say, growing without bounds. It's not being regulated. So the system is not bounded. So it is a non-regulation condition. The opposite, of course, is when it is regulated. So a condition for systems that have a limited response for a sustained change in input, meaning the response is bounded. It has limitation. It does not increase exponentially or decrease exponentially, but rather it has set boundaries. If that is the case, then your system is said to be regulated. Now, since you are already familiar with the different transfer functions of the other physical systems, and even more so familiar with the linearization required for systems modeled using non-linear differential equations, you are ready now to apply what you've learned in the representation of the different types of input to the transfer functions of these systems. That way, you'll be able to know how will your control variable respond to these different types of input. So that would be our next goal. As for now, I'd like you to understand fully. You complement what is being discussed in this slide, what is written in your book. I will give you your asynchronous activity on Friday based on what was discussed here, and we will have feedbacking. We will have feedbacking on what you did and what you were able to understand fully and not fully on Monday. So this will be always our case here. We will be given a lecture slide on a Wednesday. You will do a synchronous task on a Friday, and we will have feedbacking on a Monday. So should you have any questions just like what we did before in the other discussions, feel free to drop in your questions in the discussion box in Canvas. So I hope I made things clear, even more clearer than before.